All right, guys, welcome to heat transfer thermodynamics demonstrations, okay? So in class, we're gonna learn that heat can be transferred in three main different ways. One is radiation, and that's without direct contact. So if I hold my hand, I've got this heat source over here. If I had this flame on, if I hold it at a distance, I can still feel the heat, okay? So the heat is traveling mostly through electromagnetic waves, okay? And it's without direct contact. Heat also can transfer through conduction, which is with direct contact. If I touch that pan, I'm going to be touching it and it's going to burn and it's not going to be good, okay? Conduction is with contact. With conduction, we get materials that are known as conductors and some that are insulators, okay? So what I'm going to do, I've got this pot of water going here, kind of heating up. I'm going to stick a metal spoon with some butter on it and a wooden spoon with some butter on it. Don't know if you'll be able to see them very well. I'm going to put them in the really hot water. I'll scoot you guys a little bit closer so you can see what's going on with the butter there. One of those materials is a conductor, meaning it allows heat to travel a lot faster than the other. An insulator doesn't allow the heat to transfer, okay? So we've got the wood one back there and the metal one right there. So just kind of keep an eye on that. I've also got these little plates. You guys will be able to feel these in class. Okay, that one feels cold to the touch. This one, a lot lighter, actually doesn't feel nearly as cold to the touch, okay? The cold one, well, this is a really good one to do in person, so hopefully you're in class, okay? If I were to predict, I would say that the cold one would keep ice solid longer than this one that feels like it's room temperature, okay? So I'm gonna put a piece of ice on both of these, okay? This is the one that feels colder. This is the one that isn't as heavy, isn't as loud, feels more room temperature, okay? I'm gonna put an ice cube on both of these. We're gonna see what happens. Don't see anything going on with our butter yet. Keep an eye on that. All right, so I'm gonna look for two ice cubes that are about the same size. It's pretty good. Okay, now again, this was the colder one. Look what's already happening. This was the one that felt like it was room temperature, okay? I don't know if you can see that or not, but it is like melting rapidly, okay? So even though it felt cold, this is metal, okay? So this is a conducting material. This is like wood or plastic, which is considered an insulating material. Oh, check out our butter. Speaking of metal being a conductor, the heat from this boiling water conducted through the metal faster and it melted the butter. The butter's still sitting up there, okay? Wood is an insulator. I can touch a wooden spoon even though it's been in hot water without burning myself. I'm not gonna touch that one because I know it's a conductor and I know the heat's gonna travel through it more, okay? This metal is also a conductor. It feels cold to the touch because it's drawing the heat out of my hand and it leaves my hand feeling cold. This material is an insulator. Look, the ice cube's still sitting there, okay? It didn't feel cold to the touch because it's not pulling heat out of my hand. It's also conducting the thermal energy from the air. So the thermal energy from the air is going through this material much easier than this material. It's going through and it's actually melting the ice from the bottom. Both of them are exposed to the same thermal energy in the air. That's not what's melting the ice. It's the material that it's on. So this is a conductor, allows the heat to travel through much more easily. This is an insulator, okay? All right, let's move these off to the side. I'm gonna turn this off. I don't need this anymore. We're gonna use butter again though, but not for insulator and conductor. All right, let's see what is next on the list. So we talked about radiation and we talked about conduction. The third kind of energy transfer is my favorite. It's convection, okay? Convection is the moving of currents. And you've heard the saying hot air rises, okay? Well, the reason is that as matter heats up, it spreads out. I don't know about you, but when I get hot, I need a lot of space, okay? If you think of the emperor penguins protecting their eggs, they're super cold and they get really close together. So matter does the same thing. When it's cold, it gets close together. When it's hot, it expands. when it expands, it becomes less dense. So we get this saying known as hot air rises. Okay, well, the same thing is true with liquids. Okay, so I have cold water and I have hot water, warm water. This is actually less dense than this, okay? Because as it's heating, it's actually expanding a little bit, okay? As it expands, it becomes less dense, so it floats, okay? If I put this on top of this, not much is going to happen. So we're going to start it off like that, okay? So I'm going to take the warm water, and I put it on top of the cold water. And you'll see a little bit of mixing of colors right at the border between the two, okay? Not a ton. So it stays yellow, it stays blue. Let me get some white paper so you can see it really well, okay? Really no separation. Now, here's the magic. I have to flip these without spilling, okay? Now watch. Okay, again, cold on top, warm on the bottom, okay? And now look what's happening. You see it mixing? Okay, look at all this green, okay? The blue, the cold on top is sinking down into the yellow, into the warmer, and the warmer is going up, and you can see the colors totally mixing, okay? This is convection. This is a convection current. As things get warm, they become less dense, okay? We can also see this. Grab this real quick. With just a normal tea bag, okay? If you take all the tea out, so you probably have some of these around your house, okay? You're gonna cut the top off, just like that. And you're gonna dump all the tea out. And so you're left with this little cylinder of really thin paper right here, okay? I'm gonna put this right there. I'm gonna move this. Okay, nice green water. All right, now I'm just gonna light this little guy on fire. You're gonna see what happens. Let me adjust this. Okay. Nothing yet. Keep watching. Whoa, there it goes, takes off. Okay. That is also because of convection. It's not that the tea bag itself becomes less dense or light enough to fly away. What's happening is the flame is actually heating the air right around it. Okay. Oh, it just came back down. There it is. It's heating the air around it. That air is becoming less dense. Hot air rises. As it burns down to just ash, it becomes light enough to be carried up with that warm air current, okay? So that's also a convection current. So because things spread out when they get hotter, we have this thing known as thermal expansion, okay? So certain materials expand more than others. Water doesn't, though. We'll talk about that in class. I'm going to save that for class time. Metals tend to expand when they get hot. That's why we have these things known as expansion joints. Construction builds thing, it has to allow for materials to expand when they get hot, okay? So I'm going to show you this in action. Another match. There we go. Okay, so I've got two metal objects here. This fits right through it, no problem, okay? When I heat this up, though, it's going to expand. It's going to get a lot hotter, obviously, but it's also going to expand the material inside of it. When it's a solid, it doesn't change the density a lot. It's the convection currents are really more with fluids, really only with fluids, with air, with gases, and with liquids. So this solid, we're not going to see a visible change, but once I heat it enough, and you'll just have to trust me on this, see that it doesn't fit through anymore. It used to fit through. Now, if I cool it off, ooh, I love doing that. It fits through again. Magic, okay? I have another example of that. It's just this little thin metal rod. I heat it, starts curling. You see it curling? And the reason is because this is actually a kind of a trick. There's actually two different metals on either side. The metal on this side is expanding more than the metal on the inside. And so it causes the pieces, the particles of that metal to spread out more, and it causes it to curve. Okay? So when I heat it, even if I heat the other side, it still curls the same way. Okay? This is a good one to put in water too. Back to normal. Okay, now that I have my flame going, I'm going to show you another experiment with insulators and conductors, okay? Metals in general are very good conductors, but some metals are better than others. So this is 5 different metals. We've got aluminum, we've got brass, which is a combination of copper and zinc. We've got copper by itself, we've got stainless steel, and we've got just plain iron. This is just cold butter on the ends of all these, okay? So I'm going to heat this up from the middle, and the heat is going to conduct through each of these metals, but it's going to go at different rates. Okay, I don't know if you'll be able to see this real well. So far, all the butter is still holding strong. Oh, there goes aluminum. I don't know if you saw that. Aluminum's gone. Oh, copper just fell off. So aluminum is a slightly better conductor than copper, but pretty close. Okay, the rest are still in place. I'm just heating the middle. The suspense is killing me. Oh, there goes brass. Yep, brass is gone. And so we're left with stainless steel and iron as the least conductive of the 5 metals that I have. Man, I'm making a mess. I don't know how long this is take. All right, well, you get the idea. Okay, so we had aluminum first, then copper, then brass. Looks like iron and stainless steel are sticking strong. All right, I'm going to stop for now because I don't want to oh, there went the iron. Iron fell off, stainless steel is still there. That butter is now in my shoe. That will be fun. This is a known quantity with metals. We can measure how conductive they are. It's known that some metals are more conductive than others, and kind of their ranking. I just want you to see that different conductive rate. Let's see, thermal expansion. We did the melting ice. We did the flying tea bag. I think we're good. Heat.